Next up, we have Minh Nguyen, who's going to talk about the neural rendering model coming from Rice University.
Thank you. All right, so hi everyone. Today I will present our latest work on the neural rendering models, which is a joint generations and prediction approach for semi-supervised learning. And we also go beyond semi-supervised learning to try to explain a little bit about the architecture of deep neural network. All right, so we all know that deep learning methods achieve like step-up performance on a wide range of perceptual inference tasks. And in my opinion, there are three main factors that account for the success of deep learning. First, the massive amount of label data, big computer, and efficient framework to implement DeepNet. Looking ahead in the future, for more success deep learning, I would argue that the later two have already like quite good solution. However, the bottleneck will be the massive amount of label data required to train a deep neural network because it's often very costly or sometimes infeasible to annotate the massive amount of label data. So among the approach to overcoming this limitation is to do semi-supervised learning, in which you learn from both labeled and unlabeled data. To learn from unlabeled data is challenging. And one potential solution is we want to somehow exploit the structure in the data in order to facilitate the training. And in our project, our solution is we want to develop a generative model that can capture important structure in the data by taking advantage of the deep neural network. And the philosophy behind this is if we believe that the deep neural network can build a posterior of the label given a data, then the question we want to ask is what is the likelihood of a data or the data given the label look like if the posterior is a deep neural network? And why we want to do that? Because if a neural network achieves very good performance on some like predictive tasks like classification or segmentation, then we hypothesize that the architecture of DeepNet somehow implicitly capture some important information about the data and the image. All right, so to sum up the big pictures, if deep neural network do inference, what should be the generation underlying this inference process? And there is multiple benefits of figuring out this model. And I want to emphasize that it's not only about semi-supervised learning. So definitely semi-supervised learning is one application we want to target for. But with this model, we can also explain a certain operators in DeepNet, and then we can answer the question, what are images to the CNN? Or in other words, what is the optimal signal class that the CNN work the best? All right, so we name our model the neural rendering model, and in the next section in my talk, I will explain the model and then try to connect that to semi-supervised learning and offer some future works. Okay, so neural rendering models is a multi-scale model in which we try to render images via multiple layers of abstraction. So we start from the top of the model with the class label Y, and then using the class label, we select a template for the class. Let's say a high-level cat or a high-level dog, right? And then in subsequent layer, we introduce more detail into this template by using a rendering matrix, which is again selected by a set of pattern variables at each layer. So at the end of the process, we add pixel noise into the render image. So mathematically, the rendering process can be summarized by the equation. So first, we sample the latent variable from a categorical distribution. And the interesting thing here is we kind of like design this prior distribution in the sense that we can capture dependencies between latent variable and allow us to reverse engineer the DeepNet. And then we use the latent variable to select the rendering matrix. And the final image is the product of the class template and the rendering matrices with the additive Gaussian noise. And here is the formula for our, we call the random bar score, which we use to compute the prior distribution of on latent variable in our model. Okay, so now let's look more into like one single transformation from layer L to layer L minus 1 in our model and explore what kind of latent variable we use and what is the rendering matrix we use. So there are two sets of latent variables that we use. The first one is a binary vector, is a binary latent variable, which select, which decide if we want to render at particular pixel location or not. And then the second set of latent variable is the local translation latent variable, which decide if we render where we want to place the template. So to some extent, one layer in our model is quite related to this Spark coding model, which is the more information about the location of the rendering where we play the template. Okay, so with this rendering framework, and if we do inference in our model, we can recover the DeepNet, and we could establish the one-to-one correspondence between operator in DeepNet and the latent variable in our model. So for example, we can prove that the ReLU function in DeepNet will corresponding to doing max inference of our sparse latent variable, which decide render or not, and we can show that the max pooling operator in DeepNet will correspond to the local translation latent variable in our model. All right, so in summary, we have given a DeepMath inference process, we develop a generative model that helps us reverse engineer DeepNet and provide explanation on certain operator in the deep neural network. Question?
Sorry, so for your rendering model, it's all a linear transformation? All these steps, these big lambdas are all linear?
Yes, it's all linear.
So the rank of your representation can never grow beyond the rank of your output?
Yes.
I guess that's not an issue, though.
Yeah, so if we look more into this linear transformation, this is quite complex because we have like the local translation matrix and some zero banding matrix. But you're right, so the rank is be limited by the size of the output vector. Okay. So we talk about inference. We talk about the rendering model. And now the next question is how can we learn this model? In other words, what is the objective function we use to optimize this model? And like other generative model, we want to optimize the likelihood, right? So if we have the labeled data, then we optimize the conditional log likelihood of the model. And if we have unlabeled data, then we optimize the complete data log likelihood of the model. And we saw the correspondence between the likelihood of the model with the popular losses people use to optimize DeepNet. So for example, if we optimize the conditional log likelihood of our model, that corresponding to this cross entropy loss we will use to do supervised learning. And if we optimize the likelihood of our model, which corresponds to the reconstruction loss like autoencoder, and an extra term we call the random path normalization, which captures the prior distribution of all latent variable in our model. Okay, so now we talk about inference learning. And we have a model that kind of reverse engineer DeepNet and also explain some losses we use to optimize DeepNet. So what can we do with this? How can we use this model to improve the current DeepNet? So we explore this question in multiple ways. First, we want to develop a better loss to train DeepNet. So according to our theory, the cross-entropy loss people use to train DeepNet is the lower bound of our conditional conditional log likelihood. And we can develop a better lower bound. And the way we develop it is we introduce a new branch into a deep net, which we call the minimum branch, which share away with the original branch. However, we invert the operator. Instead of max pooling, we use minimum pooling. And instead of prelude, we use the opposite version of prelude that pick the negative part of the signal. And we compute the cross entropy for this branch, which we call the minimum cross entropy. And we combine the max cross entropy and the minimum cross entropy to develop to arrive at the better lower bound for our conditional log likelihood. And I will show that this new architecture, which we call max-min neural network, will help improve performance in semi-supervised learning. Second, we can use our generative model to analyze the performance of deep net. In particular, we can prove that the deep net, we can prove the convergence property of deep net, and we also develop a generation bound for a deep net, which is proportional to the number of active rendering paths in the model. And by active rendering path, I mean the path that connect these neuron, the activation at the top of the network to the pixel of the image. And whenever you have a value that turn off one of neuron, then the path is inactive. So the active path will contain all of the active value. And we compute that across the, on average in the training set, and we get one number, and that will affect this generation bound. I want to emphasize that this bound might not necessarily be better than the existing bound. We just try to offer a new perspective to understand generation bound of deep net.
Is the average number of rendering paths or worst case?
Average. Yes. Expectation over one of these images. Okay, and we try to showcase our model for semi-supervised learning task. So we observed that when we concatenate DeepNet with our neural rendering model and the max-min architecture, we actually improve the static arc in semi-supervised learning on Cypher 10, Cypher 100, and 3HN by a significant amount. I mean, 0.7 and 1.8% here seems small, but in semi-supervised learning and on top of static arc, it's quite challenging to achieve. Also, our methods, the max-min network, also help improve static arc on Cypher 10 and ImageNet for supervised learning also. Okay. Now, we have a little bit more understanding of DeepNet, and we saw some small improvement over DeepNet and get good results on semi-supervised learning. So what next? How can we go forward from this point? So it turned out that in our neural rendering model, when we do inference, we need to make an assumption that the intermediate render image in the models is non-negative, so that we can do maximum message passing in the inference. That assumption is a little bit impractical, because in practice, when you observe the activation of the render image, they are not always positive. So that limits the performance of our model, and in turn limit the performance of DeepNet. So we want to relax that assumption and develop a better inference, aka better DeepNet. So this work we call convolutional neural network with feedback, and it was done mostly by Yucha and Sophie, also in the audience here. So the idea here is we want to do iterative inference with our neural rendering model in order to improve the inference and improve the robustness of our method. So a little bit on the motivation. So we know that DeepNet is very sensitive to changes in the input data. If we add noise in the image, or we blur the image, or we took out some pixel in the image, the performance of DeepNet will drop significantly. However, for human, even the baby can be more robust than neural network under this situation. So the question is why, what in the human brain that helps us more robust to degradation in the data, which is currently missing in a deep neural network. So it turned out that in human brain, in addition to the feed-forward connection, we also have feedback connection. I kind of try to denoise some, try to clean up the estimation from the feed-forward step. And this feedback connection is currently missing in DeepMath, or at least the traditional DeepMath that we know. And in our project, we try to introduce the feedback into our DeepMath using the neural rendering model. So we can consider the CNN as the feed-forward connection. And we can use the neural rendering model as a feedback connection to provide feedback signal to the CNN. However, currently, the two bus are not connected, right? Because we only do like feed-forward, and then we do feedback, but we don't have the connection, we don't have like the link between the feedback to the next feed-forward. So solution is very simple. We just link them together. So and here is the iterative process. We do the CNN to do forward estimation, and we use the NRM to provide feedback signal, and we send that feedback signal back to this forward connection into the CNN and do it iteratively until conversion. So usually like, it takes around 10 iterations to convert to some extent. And the interesting thing here is when we send the feedback signal back to the CNN, we also modify the non-linearity. Instead of ReLU, we actually develop we call adapt ReLU and adapt pooling, which use information in the feedback signal to update activation in the feed-forward step. And we do some initial experiment to showcase the promise of the model. So in this experiment, we try to recover the clean data from degraded data, which can be noisy data or blurry data or occluded data. And the performance here look promising. And I want to emphasize that in the experiment, we don't train with the noisy data. We train with the clean data, and the model automatically know how to recover the clean data from the data from other distribution. And we also show the robustness of our methods under this degradation. So the original CNN have like significant performance drop when you have noise and blur and occlusion, but our model achieve much better accuracy with smaller performance drop in those situations. And this is the initial experiment on MNIST. I know that there is more things to do on at least to scale up to Cypher 10 and ImageNet, but this is initial promising results. Okay, so to sum up, in this work, we developed a neural rendering model that tries to reverse engineer DeepNet and provide a way to for us to analyze the consistency guarantee, conversion guarantee, and Johnson bound of the model. And then using our neural rendering model, we propose a max-min network that helps us achieve very good results on semi-supervised learning tasks and improve results for supervised learning. And we also developed the convolutional neural network with feedback in order to improve the robustness of the classification. For future work, we want to extend this model for dynamic setting and also use that for the R distribution detection. So actually, we have some initial results for this, and you can check out the result for early detection in our paper and explore different noise distributions. So currently, we're using Gaussian, but potentially we can use other noise with heavy tail, like Laplacian and student T. And for robustness, we want to see if the CNN with feedback can be robust to adversarial attack or not. And we want to draw more connection between our models and some mechanism in the visual cortex. Bigger picture, so the NRM provides us like a model for images, like what are images to neural network, right? We also want to understand what is the functional class represented by the neural network, and then the interaction, like the relationship between this functional class represented by DeepNet and the model class from our NRM, who can help us to understand better why the CNN work. And I want to acknowledge Zach Bitkow, Gautam Dasarati, and Florence Straffer for their comment and feedback on the project. And yeah, and my group, the SP group, and Professor Animan Al Lab at Caltech. And thank you so much for your attention.
We have time for a few questions before the break.
Referring to the last topic, where in your scheme do you get the complete image?
Say again.
You have an architecture where you have feedbacks.
Yes.
Where in this architecture do you have access to the image that has been filled or cleaned or recovered? Where is it?
Yes. So, yes, in the architecture, in the first iteration, we have a clean input, and we send the input through the CNN to collect the value for latent variable. We use that value and send that through the NRM to reconstruct the image. That's a cleaner version of the image. And then we send that cleaner version through the CNN again and do it again and again. So we only use the clean image to train the model. And then in the test time, when you have the noisy image, then we send the noisy image in the first iteration to the CNN and do the same thing. And after each iteration, the noisy image becomes cleaner. And that's our belief of why this works, because after one iteration, you clean the image more and more. Thank you. Yeah, and I want to mention that this might not work for adversarial attack, because the thing is, for adversarial attack, right, you change the label at the top. So after the first iteration, you might use the wrong information to reconstruct the image. However, some initial experiments showing that if we weight the different iterations properly, it's still robust to adversarial attack, and we so far don't really understand why. So more work needs to be done.
Okay,
Thank you.
great. We're going to take a short break.